Hi everyone and welcome to Nanotalks. My name is Ryan Ramsey and today we have Hugo Perez on from DENSsolutions. Say hi Hugo.
Hi, good morning, everyone.
So Hugo, do you want to tell us a little bit about what you'll be presenting today and your history?
Yeah, sure. So the idea of this Nanotalks is basically to give the audience an idea or an introduction to a slightly more advanced and more reliable way to prepare the lamellas, mainly for the in situ experiments that everybody here is particularly interested in. And the idea is basically to show or to introduce a new method that will be easier and that will be faster. Now, regarding my history, my background is in mechatronics engineering. I hold three different master degrees. The first one in molecular bioengineering from TU Dresden in Germany. The second one in nanotechnology from Chalmers University in Sweden. And the third one, which is an MBA from Cambridge University in the UK. And about a year ago, I finished my PhD at TU Delft, which was basically developing different types of nanotools for applications in micro to zepto fluidics and graphene technologies. So that's pretty much what I've been doing.
Keeping yourself busy by the sounds of it.
Yeah, a little bit.
Very impressive, obviously, and congratulations on your new son only 6 months ago.
Yeah,
So
thank you.
just adding to the long list on that resume of yours. Okay, so you're now working with DENSsolutions.
Yes.
Do you want to just tell us very quickly what you'll be doing with DENSsolutions before we kick off?
Yes. So I'm basically the microsystems manager, and that means that I'm responsible for everything that is related to the MEMS devices, or the nanochips, as we call them. Nanochips, the nanocell, the nanoreactor, everything basically that comes down to the chip level. That is my main responsibility. So going from the design of the chips, managing the microfabrication, basically going from specs to final product. But everything surrounding the chip or the MEMS device. So that's mostly my main focus within the company.
Okay, great. Well, let's take it away.
All right. So yeah, we're gonna start quickly by introducing the FIB. I'm pretty sure that everybody here is familiarized with it. But basically, the idea is that inside the FIB, you always have an electron beam, which is at a 52 degrees angle, as you can see here from the ion beam. Now, typically, this ion beam works with gallium ions, and the idea is that this ion beam can help you to either do some trenches to mill something, but it can also help you to induce the deposition of different materials, let it be TiOs or platinum, which is the conventional one. Now, one of the main issues when it comes to sample preparation is the fact that, first of all, it's a very slow process. Typically, to prepare a lamella, it can take up to 4 or 5 hours. And the other thing is that there's always a certain risk involved when you're transferring your lamella from the sample to your chip. However, we have to take into account that this transferring process also requires typically an intermediate step that you use to rotate the lamella 90 degrees so that you can place it in a parallel fashion on top of the nanochip. And during these steps, you can typically lose the lamella. So these are different types of problems that people usually want to get rid of. And of course, one of the most annoying ones is coming from the platinum deposition as well. And that is because when you do the final thinning, there's always a risk that if the platinum is facing the ion beam, you would start spreading the platinum on top of your sample and contaminate it. So this is also one of the main issues that you want to solve. Now, this process, what it does basically is that it allows you to tackle down these kind of problems. So what we do is we have developed this custom-made stub, which, as you can see here, it contains a 45 degrees angle on both sides. Now, the idea is that you place your sample on one side and you place the nanochip on the other side. This stub, by the way, has been designed in such a way that it could be compatible with all of the different types of chips, let it be the nanochip, the nanoreactor, the nanocell. And the idea is that we use or we take an advantage of these angles so that you can basically transfer the lamella in a much easier way. So then what you see here, this is on the left side, the real life picture. You can see the sample from which we extracted the lamella, and on the other side we have the nano chip, and here you see them directly underneath the electron beam and the FIB. Now the first thing that we do is we introduce this, of course, inside the FIB, and since the sample is located at a 45 degrees angle, and you typically want to create the lamellas at a perpendicular angle to the ion beam, then the first thing that you will have to do is to tilt this top 7 degrees to complete basically the 52 degrees. Now at this point you will be completely completely perpendicular, sorry, to your sample, and that's when you can start introducing the Gis needle to start the platinum deposition.
On the Gis needle, actually, could you just elaborate a little bit more on how exactly the Gis needle does work?
Sure. So basically, the Gis needle, it's a needle that introduces a gas. Now, this gas is a precursor, as we call it, in order to induce the deposition of the platinum. Now, this precursor gas basically consists of a tetramethyl platinum precursor, which means that there is a platinum core surrounded by 4 methyl groups. Now, the idea is that this Gis needle is constantly supplying this gas all over the surface of your sample, and using the ion beam, you can basically define the area where you want to deposit the platinum. So then what the ion beam does is that it breaks these molecules, and because the methyl groups are very volatile and the platinum is not, then the platinum will end up basically depositing or sitting down on the surface, while the rest of the volatile groups, so the methyl groups, will get sucked out of the chamber because you're in vacuum. So basically, by doing this, you can control the amount of platinum that you're depositing and the shape of the platinum that you want to end up with. So that's roughly the way the Gis needle works. So then by using this kind of principle, we can start depositing the amount of platinum that you require, which typically people use a width of 2 to 3 micrometers with a height of 2 micrometers and a length of 8 to 12 micrometers. Also for this method, we found those to be the ideal dimensions of the platinum. So at that moment, once the platinum has been deposited, we can basically start the regular process to create the lamellas. So that means that
Before we actually go into the next step,
sure.
Could you just, is it actually necessary to deposit platinum?
That's a very good question. Actually, the platinum is the main cause of most problems because, as I was mentioning, the platinum could be the main source of contamination for your sample. Nevertheless, the platinum deposition is only valid if your sample has a thickness below 500 nanometers. And that is because if your sample is thick enough, so above the 500 nanometers, then you can do the milling without going into the risk of completely etching away your sample. And that is actually the main reason why we have to deposit the platinum in thin samples, because the ion beam basically will start shooting or bombarding everything that is around. So if your sample is very, very thin, you will also end up bombarding it and etching it away, essentially. So if you have these kind of very thin samples, then depositing the platinum ahead of time helps you to prevent the ion beam from attacking your sample. But as I said, if you are working with a sample thickness above 500 nanometers, then the damage that the ion beam will cause will still give you room to end up with some of your sample underneath. So in that case, it wouldn't be necessary. But in most of the times, samples are typically below 500 nanometers, and that is why the conventional process requires the platinum deposition. So then, as I was saying, as you would normally do, you would start by doing the front and the back side milling to create these trenches, as we can see here. If we look at this image, B, you would see that there's this sort of a stair effect. The only reason why we did this is not necessary per se, but the reason why we did this is because you can then divide the process into steps, doing this front side milling and then this other one here, which would be much faster than if you want to mill all this volume at once. So it's just simply to save some time. And then you basically start doing the trenches, and as you can see in this image, we typically also do a little trench on the side of the lamella, leaving something as you can see it right now.
But actually, this image or these two images does show it's a little bit interesting to me. In my experience, you actually have the platinum across the whole lamella there. Now, in this particular image, it doesn't seem to go the whole way across. Can you just explain why that is?
Yeah, that's true. That's also a good observation. The main reason why we do this is because it is true that you can typically have the platinum all over the lamella. Now, I was mentioning at the very beginning that the normal dimension, the usual dimensions that you would go for are 8 to 10 microns in length for the lamella. So that's basically the length that you see here. But we recommend to leave these additional protrusions because then that makes it easier for the user to handle the lamella, and that is because you can basically insert and weld your OmniProbe into one of these protrusions instead of the main part of the lamella. So then the whole process becomes a little bit more robust, and then you protect the integrity of your lamella even more, which is of course a very important thing, particularly if you're going to be working with very thin lamellas at a certain point. So it just makes the whole transferring process much easier. And that is, by the way, the same reason why we create this side trench here, because we basically give additional space for the needle, for the OmniProbe to enter and then weld it on the side of the lamella. So basically, once you have done this, you can basically do some over tilting of the stub so that you can do the undercutting. Now, that is also the main reason why we needed to create this additional space in the front trench, such that the ion beam, which is coming from this side, can have access to the bottommost part of your lamella. So then at this moment you can do the undercutting, which you can see here. And since the lamella has been undercut, then it's basically released from the front, from the back side, from the side, and it's only hanging from this little side here. So that will be the next thing to do before you can release the lamella. Now, one of the things that we recommend at this point is that you can start doing the so-called pre-thinning of your sample, such that the final thinning can be much faster and a bit easier to do. So then if you initially had this thickness of this width of, let's say, 2 microns for your lamella, you can start doing the pre-thinning and bring it down to, let's say, 100 or 200 nanometers in thickness. And at the same time, we recommend to do the pre-thinning up to a certain depth. So as you can see, we leave this bottom part, which is thicker, and because you basically have this frame coming from the protrusions that we were talking about earlier, and this thicker part that is at the bottom, then you know that you can handle such a thin lamella in a much more robust way. Otherwise, the lamella can just be flickering around, and you can potentially lose it when you weld it somewhere else. So then after you've done this so-called pre-thinning, then that's the moment when you can introduce the OmniProbe to release and to retract the lamella. Now, what we do is we introduce the OmniProbe. Here's a real life image of how it looks like. And here you can see the importance of the side trench, because then we're giving additional space for the needle to enter. And here you can also see the importance of having the protrusions, because then you can weld the lamella there and you still have complete access to inspect your lamella or the thin region at all times. So as you would normally do, you insert the OmniProbe, you induce the platinum deposition to do some welding, you release the lamella from the side, as you can see here, you just do the final cutting, and then you just do the lift out. So at this moment, your lamella will be completely parallel to your nanochip, and that is then the main advantage of having this 45 degrees angle on the stop. So if you have a 45 degrees angle for your sample and for the nanochip, it means that in between both of them, as you can see here, there will be a 90 degrees angle. So because of this 90 degrees angle, your lamella will be completely parallel to the chip. So that means that you can just take it away from your sample as you retract it and transfer it on top of your chip. So then as you took it out from here, you just need to lower down the stage or the stub move it a little bit to the right, and then introduce again the needle with the parallel lamella, and you will be directly on top of the electron transparent window.
Actually, one question which may come up is that I know that some omniprobes and some FIBs actually can rotate.
Yeah, that's true.
Is that necessary in this particular process?
No, that is actually one of the added values of these kind of processes. That because of these kind of angles, you don't need to have the rotation capability of your OmniProbe. The rotation capability that the OmniProbe offers in certain machines is basically to facilitate the user the transferring process of your lamella, such that you can place it in a proper angle, let's say. But because here you are already in a parallel angle to your chip, then you don't need absolutely any type of rotation. You just need to insert the probe, weld it, retract it, and then just lower down the stage, move it, in this case, as you see in the image, towards the right, insert again the probe with the lamella, and then you will be already completely parallel to the nano chip. So then at this moment, you can just keep on bringing the lamella until you're on top of the electron transparent window of interest, and then you just place it on top. So then as we said, because the lamella is completely parallel to your chip, you can place the lamella, and it will be laying down completely on the surface. So then there won't be any risk that you would potentially lose the lamella, and then you can just secure it by welding it on the corners. Now, as opposed to traditional techniques where you typically have to use an intermediate tool for you to rotate the lamella 90 degrees, and normally when you do this, you have to weld it only on one side, and you can lose it, you have to vent. Here, you can basically just do the transferring right away without having to vent, and having the lamella completely laying down on the surface. Now, at this moment, as you see, the platinum is basically facing the ion beam. Now, this is one of the main questions that might come up, and that is with regards to the final thinning, because this is basically the moment where you can start doing the final thinning. Now, in principle, we were mentioning earlier that if you want to start the final thinning, and if the platinum is facing the ion beam, you can potentially start dispersing the platinum all over your sample and contaminate it. So then there are two things that you can do. One, you can basically rotate the chip 180 degrees so that the platinum will be on the opposite side as it is shown here, and then the ion beam has access to start doing the final thinning without the risk of spreading or dispersing this platinum. Or two, to do the final thinning from this side where the platinum was. Now, in our case, we wanted to explore both options to try to offer as many as many options and as many possibilities to our users. And what we found is that you can actually do the final thinning as well, even if the platinum is facing the ion beam. So as you can see here, this is the image of the lamella after it was welded on top of the electron transparent window, and these arrows point out the direction of the ion beam. So then you can see that the platinum is facing it, and this is an image of how the lamella looks at the end when it is thinned down to 20 or 30 nanometers. So you can see that it's almost it's pretty transparent because of that. Now, one of the things that I was mentioning is that ideally you would like to rotate this 180 degrees, and in that case it will be like this. So you see that now the platinum is on the opposite side, and the ion beam is entering through the substrate. So in this case, there was no risk at all points to contaminate your sample. But basically, by following, as we show here, these kind of tilting angles, you can achieve the final thinning even if the platinum is facing the ion beam.
And so that does then avoid any contamination, because obviously the ion beam facing the platinum here, that won't actually disperse platinum over the sample itself.
Well, in principle it would, but then what happens there is that the amount of platinum that is dispersed or that is contaminating your sample, you can actually get rid of it eventually. One of the tricks here is that this sample is located on the nanochip, and the nanochip is a device that you would use to heat up your sample. Now, the platinum happens to be a very mobile element, even more mobile, for example, than gold. So then if you did the final thinning in this manner, and if you have potentially some platinum contaminating your sample, by the time you do the experiments, you can do some preheating at, let's say, 150 or 200 degrees, and this actual will bring enough thermal energy for the platinum to start moving away from the area of interest. So then that is actually one of the main tricks that most people don't know, that this platinum happens to be so mobile that if you do a little bit of preheating before you start the experiments, and preheating 150 to 200 degrees is considered still to be a low temperature, let's say, and by doing that, you can basically, as I said, give this thermal energy for the platinum to move away.
It's actually a similar trick I know of, is just the contamination from the E-beam when looking at samples, a variety of different materials. It's the same process, heating up to around about the 150, 200
Exactly.
will remove that contamination and give you a much clearer image.
Exactly. So that's pretty much an analogy of what happens in this case. Now, one of the key things to achieve this kind of final thinning, and that is, as you can see here, is described. When the ion beam basically is hitting your sample to thin it down, what we do is that we start doing small changes in the angle. So we start playing with the tilting, and we go from 12 degrees to 9 degrees. So then if you go from 12 degrees to 9 degrees, that means that you can use the ion beam to mill a little bit of the front part of the lamella. Then you go down to 9 degrees, and then you start milling the bottom part of the lamella, and that's also because you have access through the hole of your window. And in that way, you basically don't do the final thinning only from one side, but you have the control of doing it from the top and from the bottom. And this allows you to spread less platinum, and also to control the amount of damage that you can potentially create. Um, but of course, as you see here, the easier alternative as well would always be to rotate the chip 180 degrees, so that the ion beam is not facing the position. And this would also ensure, of course, from the very beginning, that your sample will be contamination free. So that's basically how this method works. So with that, I would like to thank you all for your attention, and not before, of course, acknowledging all the people that participating in developing this methodology.
Great. Well, thank you so much for coming on board. I do have a few more questions.
Sure.
I know you were working on a new FIB process.
Yes.
Could you tell us a little bit about that? I know it's not ready as yet to be announced, but yeah, just elaborate on how that changes.
Yeah,
from
sure.
this one.
So, for example, as opposed to this method that we just discussed, the new method will aim at solving basically all the main problems that a user could face from the very beginning, and that is, for example, normally, and depending on the experiment, you could be potentially interested in having your sample already in the correct crystal orientation for you to prepare the lamella. And basically, what this new method would allow you to do is, from the very beginning, the step will be a little bit different, and it would allow you to mount two or more different types of sample. Then once you have the samples mounted on this new stop, you would be able to locate them in the right crystal orientation. Then you can transfer lamellas in up to 4 different nanochips. So that means that you can prepare more lamellas and transfer more lamellas within the same process without having to vent even once. Then, of course, the other important part is that as opposed to this method where you would in principle have to rotate 180 degrees the chip manually in case you want to have the platinum on the backside. With the new method, you would be able to do the rotation of the lamella from the very beginning without having to vent, so that you can rotate the chip. Another advantage is the fact that you would also be able to have this parallel angles between the lamella and the chip, so that you don't have any type of risk of losing the lamella when doing the transferring step. And also the additional advantage of having some windows. The stub would basically have some windows, so that your sample can have direct access to the stem detector in case your FIB machine has one, so that you can do some further nano analysis of your already thin lamella. So then the idea of this new stub is that from the very beginning you can do, as I said, the crystal orientation. You can you can find the right crystal orientation. You can transfer 2 or more different samples in up to 4 different chips. You can do the transferring, you can do the rotation of the lamella, and then you can do the nano analysis, all of this without having to vent even once. So we do expect that this new method will bring even more added values to your research, and not only in terms of less risks, but also in terms of the time that you require to prepare all the samples. So yeah, that is almost ready. So just keep an eye on our website, keep an eye on the Nanotalks, and soon you will be able to hear a little bit more about it.
Right, well, I'm sure all the listeners will be very excited to see that new update. One last question. This was very much focused on the wildfire heating nano chip.
Yes.
Does this apply to, I guess, all MEMS devices, or?
Yeah, absolutely. So this is a very general method per se, in the sense that well, in this video and in these slides, we were showing mostly the nano chip. But the stub has been designed in such a way that it is compatible with all the different types of MEMS devices that we offer. Let it be the nano reactor, let it be the nano cell, let it be the chips that we use for biasing. And it actually allows the user, or it empowers the user, to go beyond the chips and the MEMS devices that we offer, and they can also use it for any other potential chip that they might have around, or wherever they want to transfer the sample. So it all comes down to a very general way to prepare the samples, to transfer them, regardless of the chip where you want to transfer the lamella, but having as the main point to make it a quick and reliable way to prepare the lamellas, basically.
Great. Well, thanks so much for coming on, Hugo. We'll have Hugo's details on the website following the webinar. So if you do want to contact him, do write in with any questions you have. We're obviously all about trying to support the sample prep process. And yeah, we hope to get you back on to share the new update.
Yeah, certainly. I'm looking forward. I do expect that it's going to be ready in just a couple of days from now. So yeah, certainly Ryan will keep us all updated with that.
Great. Well, we'll definitely touch base about that. Well, thanks to all the listeners for joining us on episode 3 of Nanotalks. And don't forget to register for automatic updates on the Nanotalks webpage on the www.DENSsolutions.com/Nanotalks. And Nanotalks brought to you by DENSsolutions. DENSsolutions offering you in situ solutions for microscopy with heating, biasing, gas and liquid systems. To find out more, visit DENSsolutions.com.